Okay, so the next section here out of abstract algebra is about data workflows. And, frankly, this is a little bit more of the soft skills, but again, it addresses why are we doing this advanced math, but in the context of data workflows. So, taking a look at our example company, foodbartender.io, we've got a hypothetical here we're going to consider. Foodbartender.io just hired an engineering director, new engineering director, and her first priority is to get the company's data science efforts initiated. So there have been several concerns that were voiced by the team prior to making this new strategic hire. Number one, people are getting the idea that data science teams are interdisciplinary. That is to say, you've got your analysts working alongside with some ops people, alongside some business people and some programmers. You end up having people from very different backgrounds, people working in very different kinds of roles, needing to collaborate together, ultimately on the same code, the same work product that you're going to have. So you've got this interdisciplinary team aspect. Number two, another problem is that it's really great to be able to run your code on 5,000 servers. Running your code on 5,000 servers is actually kind of expensive. The thing about servers is they do take a lot of power, and they also take operations people to run them, and they involve some pretty costly facilities, data centers. So clusters are expensive to operate, and even more so, maintaining the apps that run on clusters, that's expensive, especially as the company scales up over time. And that's been my experience with leading data science teams, is that maintaining the code on the clusters or debugging the code even as it starts to get rolled on the cluster, that's usually your biggest pain point. Another thing that's been voiced by this team, and again, it's something I've heard over and over, is that it's not quite clear what kind of open source frameworks need to be used. I mean, everybody's talking about Hadoop, and then other people are talking about Spark and Storm and HANA and gosh, all kinds of things. Maybe some of them aren't exactly open source. How do they compare? And another thing too is the company is looking at the fact that, well, they've done a lot of batch processing, but now they want to do some more real-time processing. And how do those fit together? Okay, can you use the same code in batch as you would in real time? Do we have to switch off the frameworks and rewrite all of our code just because we're moving from batch to real time, etc. So three concerns there. Interdisciplinary teams, clusters are expensive, and it's not clear what the system architecture or priorities are going to be. You want to have room to grow. So let's talk about team. Here's what I use a whole lot in business to be able to try to convey how do you build a data science team. I usually think of 4 different roles. So number one, there's a domain expertise. There's somebody who represents the stakeholder, who's very familiar with the business process. So for instance, if you're working in finance, business process means you understand about audits, you understand about regulatory issues, you try to understand what is it that the bank is trying to achieve with a particular product. Another type of role, of course, is data scientist, the analyst. There's a lot of names there, but you're basically doing the same thing. You're doing data preparation and discovery and modeling and a lot of the quantitative kinds of things, visualization, etc. And then on these teams, I usually stress the point that there's 2 other roles identified. One is your application developer, the person who knows about software engineering and those kind of practices inside of the organization. Essentially, how do you automate things? And number 4 is more of an operational role, people who have the expertise in systems engineering, essentially running the clusters, how to make sure that the apps that are running on the clusters are highly available. When I'm building out data science teams, one of the things I try to do is to switch around the pairing. So I really take advantage of a lot of non-traditional pairing across these different roles to try to complement skill sets, really trying to tear down silos at the end of the day. So it might be, I've definitely seen the case where I take a PhD statistician alongside a Linux site reliability engineer and pair them together on a problem. And in some cases, there may be problems in terms of getting access to data where those 2 skill sets are required, And without them working directly together, the problem is probably not going to be solved. I've definitely seen those before. Taking advantage of the interdisciplinary aspects, going across those different roles, doing a lot of complementary pairing comes in very handy. And that, to me, is a lot of the essence of data science. When I talk to my other peers out in consulting work, some of the big consultancies use a very similar model of these 4 roles. Now, when I'm working on data science projects, I like to describe the process in terms of 5 steps. Number 1, when you first get into looking at a new data set, you've got a process of discovery. So that's kind of a whole big umbrella for taking a look at the data, maybe doing some descriptive stats or some simple visualizations, scatter plots, some kind of queries. I don't know, maybe you're using Hive or Shark or something like that to go in and do some real simple queries on big data and then come out with a visualization. That's typically called discovery. And frankly, for a lot of data, that's about as far as it's going to go. Just go in and look at it and see what's there. You're trying to help people ask the right question, frame the question. And I find that people who come out of business school have pretty good chops when it comes to discovery. They can make Excel do backflips. So that's the kind of idea there. It helps if you do actually have a good statistician to jump in and do discovery right and really be able to come up with some good questions to ask. Now, moving on from there, there's an entirely different step in the process that I call modeling. And it's a very different skill set than discovery. And frankly, when I'm hiring for teams, I try to really, keep this in mind, that there's going to be people who are excellent at doing statistics and discovery and visualization. They may not be the same people who are experts at doing the modeling. Hopefully you've got some overlap there, but they're really different things. And I think that's a quintessential point when you're looking here at circa 2014. One of the problems I run into in business over and over is that there's some long-standing practice of business intelligence. There's a BI team. BI is very focused on discovery, very focused on reporting. It's typically BI techniques are very light when it comes to predictive modeling. And trying to conflate those two together, mix up discovery and modeling altogether, it's what I see as an anti-pattern. It's what I see companies with BI teams doing over and over and over. And it's the business problem that I get called in to fix. So take some advice, free consulting advice here, separate out discovery and modeling, maybe back off on the BI a little bit. Modeling is about leveraging automation, basically how to place informed bets. So modeling, for instance, Google AdWords, there's a whole bunch of bets that are being placed as far as how to adjust your bid system. And that's where the money gets made. Now, down at the bottom of this, there's definitely systems. So you've got your ops people and you've got your clusters. You're taking advantage of a lot of systems engineering, distributed systems. And the priority there is to keep the infrastructure running, make sure it's cost effective. And then you've got a different type of engineering, which is your applications, working in software. You've got your Scrum teams or whatever, but people who are essentially taking the smarts out of the data science and building it into products, building features into products. I call that apps. So it's interesting that from the top we're showing analysts, a couple of different kind of analyst roles, and then from the bottom a couple of different types of engineering roles. And again, putting on my engineering director hat, you want to make sure you understand what these roles are, that you don't assign the wrong person to the wrong problem. I've seen great people almost get fired because some executive came in and put them in the wrong role. So understand that clearly, understand the different needs of a project. In the middle of it, this is kind of a key point, is integration. Being able to take the learnings and the smarts, the automation, and integrate that into your applications and your features, run it on your systems. Those two have to meet in the middle, and there's an integration process. And what I've found out of leading data teams for 10 years is that that's really where the leadership happens. Because of the interdisciplinary nature of these teams, you want the leadership to have a strong hand in terms of integration. It's a really great way as an engineering leader to understand which parts of the team are ahead, which parts are behind. Maybe there's some parts that need to be augmented or some training or whatever. But I've heard over and over reporting to CEOs of a company that, hey, look, you're an engineering director, you shouldn't be involved in like integration stuff, just delegate that. But the reality is that's where leadership really has leverage. It's a key point. So here's a model that I use to try to understand big data problems, data science problems, and take a look at sort of the cross product of needs versus roles. And I come up with, oddly enough, a matrix. So I've got the 5 different needs in my process over the top, discovery, modeling, et cetera, and then the 4 different roles. And one of the things you can do is take this and start to figure out how does the needs of my project fit versus the roles, the expertise on my team. So here, hypothetically, I've got some people that are good with discovery, some modeling, and then there's kind of a gap there, between, like, say, modeling and integration. I don't have people who have a lot of overlap there, and that's going to imply a lot more work having to be done in terms of management and leadership. So to really make an interdisciplinary team work, you want to try and close these gaps, bring in, people who have a little bit further spread across different skill sets. So doing some gap analysis on a matrix like this, I find, is a very good management tool, and I've known a number of different companies that have started to adopt this kind of thing. Okay, so those are some soft skills that are really good to use in terms of building data science teams, ultimately building workflows with big data, which is what we're trying to drive to. There's some excellent books here, actually some free books from O'Reilly. Building Data Science Teams by DJ Patil, who was formerly chief scientist at LinkedIn. Also Data Jiu-Jitsu by DJ Patil, more of the product focus. And then an excellent analysis called Analyzing the Analyzers, basically applying quantitative techniques to explore what it is that quantitative people are doing. It's by Harlan Harris, Sean Murphy, Mark Weissman, some of the folks who run Data Community DC. Excellent book there. Okay, so when I talk about data workflows, really this is about middleware. This is about a kind of evolution of middleware for big data, for machine learning, et cetera. And when I look at apps, especially out in enterprise, when I look at how this is evolving, we see the same pattern, the same kind of design showing up in many places. And it's about workflows. And by definition, workflows are a combination of automation and people. So, my daughters were kind enough to lend me some Legos here. I've got a few Lego blocks here, and I'm going to represent my data pipelines, building blocks. Remember the monoids. I've got some building blocks here, and I've got some people who plug into it. And I just want to underscore that whenever we talk about workflows, we're combining automation with people. So the 5 steps, let me make sure everybody's standing up here. Okay, stand tall. The different 5 steps here in this workflow, typically you start out with different data sources. Maybe you've got some customer profiles, maybe you've got some log files, you've got different types of data sources, you're going to bring them together. So number 1, you're starting out with a variety of data sources. And that leads to a lot of problems because they're probably coming off of different types of storage frameworks, they're probably in different formats, et cetera. So your team has to grapple with that, bring the data together. Usually there's some kind of process of loading that up into a cluster, some kind of ETL, extract, transform, load. Some type of ETL that's being done to get your data all into the cluster. And that's an expertise in itself. And then from there, actually if you look back at the book I was referencing earlier from DJ Patil, the step of preparing your data, cleaning up your data so you can do something interesting with it, we spend about 80% of our time doing that. And on data science teams, there's definitely like a Pareto ratio, an 80-20 rule. You spend 80% of your time cleaning up the data, 20% of your time doing something interesting with it. And you just see that over and over, because as soon as you've got something solved, the senior vice presidents walk in and say, that was great, but add these other features. And now you're back to step 1 again. You clean up your data and add more kinds of data to it, and then go do something interesting. So data preparation is where you usually spend most of your people time. And then from there, you want to do something interesting with your data, probably some kind of analytics or predictive modeling, something to enrich the data, juice it up. And from there, push it out into your line of business, end use cases. So this is a general way of describing a workflow. Again, combining different teams, people, along with automation, clusters, to do these things within the context of an application. Now, a few other things about workflows. One is we're going to talk about something called separation of concerns. We try to look at the business logic for the workflow up at a higher level of abstraction and not worry as much about the implementation details. Some of the tools can handle that quite well. We'll go into that. Another thing that we tend to talk about is literate programming. Really, when we describe workflows, we're trying to describe them to other people, and you really want to put your emphasis on articulating what your business logic is, as opposed to putting your emphasis on articulating step-by-step what a computer needs to do. Again, let the compilers do that. We often take a look at visualizing the business process. It's usually really helpful on teams, especially interdisciplinary teams where you have to go across different roles. Visualizing helps people explain it to each other. And you want to leverage patterns. There's actually something called pattern language. Chris Alexander comes out of architecture, really. But it's a great way of describing best practices and sometimes describing them quite visually. How do different building blocks fit together? Again, Lego blocks. And the other point of this is that we try to take these apps and we want to run them on clusters. So we're building solutions, we have to operationalize them. That's usually the devil in the details, usually a tricky part. So taking a look at this general kind of pattern for an enterprise data workflow, we find that ETL, out in business, people use SQL, Teradata, Oracle, et cetera, things like that. Use a lot of SQL for ETL. And maybe that's changing, maybe not. But down for data preparation, big enterprise shops will have a lot of Java, have a small army of Java developers doing their data preparation. Maybe they're using SQL for that if they've got Teradata or some other big type of data warehouse. Maybe they're using Pig or other kinds of tools, but essentially that's where you start to represent your business logic. And then for predictive models, we find out that in industry, of course, SAS has a lion's share of this. On my data science teams, we tend to use open source tools like R, Python, et cetera. Definitely those are gaining a lot, but SAS is still out there for predictive models. Now, what's interesting when you look at this across industry, most of the licensing costs are going to be either in ETL or predictive modeling. Teradata and SAS, of course, holding high market share for both of those, respectively. But most of your people cost, most of your project time is spent cleaning up your data. Again, 80-20 rule. So fortunately, there's been a number of tools, mostly open source tools, that have been evolving for a kind of workflow abstraction layer, trying to tackle those problems of the licensing costs of ETL and modeling, and also the people cost of data preparation. Trying to leverage workflow abstractions so that you can cut those costs. It's a kind of big data middleware. And there's a lot of great tools that are evolving for this. I really like what's going on in terms of Python, PyData in general, scikit-learn and others. Spark, cascading, what's going on with KNIME, also over on .NET, et cetera. There's a slide deck from a talk called Data Workflows for Machine Learning. Goes into this in much more gory detail and also includes a kind of scorecard for trying to examine these different open source frameworks and see where the relative strengths and weaknesses are and how they're perhaps indicated for your use cases. So check it out.